are going to talk about rotational kinematics. It's just like regular kinematics, but spinny. It really is just like regular kinematics. It has all of the same quantities. They are just sort of doing different things, whereas linear motion is the motion of an object moving in a straight line. It can have a position, it can have a displacement, it can have a velocity, how quickly it moves along that line, and it can have an acceleration, how quickly its velocity changes as it moves along a line. And the same is true for rotational motion. You can have an angular position where you are in the rotation of the circle. You can have an angular displacement. If this thing rotates, you have rotated some delta theta. Greek party here, Greek salad. If you are rotating at a speed, you have a rotational velocity. That is the Greek letter omega. It looks like a butt, but give it the respect it deserves. It is definitely not a W. I say that after calling it a butt. And there is rotational acceleration, where the speed of the spin of the object can vary over time. So it can spin up or spin down. It can accelerate its rotational speed, or it can decelerate its rotational speed. And so as a visual example of that, we've got this little doohickey, which is a little person, and there's these spinning bars, well, non-spinning, but you can see real tiny rotational velocity. And if I bring up the slider, you can see I brought it up to a value of 2.7, but it takes a while to get there. And so that little red number right there is its current rotational speed, and it takes a while for it to spin up. And if I bring it back down, the rotational speed decreases, and so it's undergoing a rotational deceleration, shall we say. This device is called the rotational motion apparatus, aka the spinny thing. What this spinny thing allows us to do is to analyze rotational motion. In particular, this is a 1 radian sector, and using Logger Pro and this photo gate, which will be either blocked or unblocked by the presence of that cardboard as it swings through the gate. As you can see, it's blocked there and unblocked there. It will take that information. I've calibrated Logger Pro to know that anytime that the sensor is blocked, that is a distance, quote unquote, of 1 radian. So that's a 1 radian sector. It is a sector of a piece of pie where the radial, where the arc length is equal in length to 1 radian. So if I took this 1 radian and put it over here, look at that. That is an arc length of 1 radius. That's what a radian is. And so when I spin this, if I clear my data, I would like to clear all data. If I collect data and then give this a nice little spin, that sound you hear is due to a little plastic screw which is making contact with the spinning plate, causing this to slow down ever so gradually, and allows us to see a graph of velocity versus time. In this case, we're talking about angular velocity, a number of radians, or a number of how far of a rotation it completes each second. Another good example is this ladybug PHET demonstration, where this one actually says the angle. Now this one says angle in degrees. Most of the time we're going to be using radians, and it gives an angular velocity in degrees per second. We will be using radians per second, which at first may sound a little intimidating, but radians to degrees is simply a conversion of, there are 360 degrees for every 2 pi radians. So it's basically just a unit cancellation conversion kind of thing, which we'll take a look at in a little bit. But so we got this ladybug right here, and if I move this platter, grab the handle and move it, I've now just moved the ladybug through an angle of 52.98 degrees. And if I go around, all the way around, as you might expect, it's going to be about 360 degrees. But if I keep going, this is the thing about rotational displacement, it keeps adding up. We've gone through 1 circle, 2 circles is 270 degrees, 3 circles, 4 circles, 5 circles, and so on. So the rotational displacement keeps increasing. Oh, I let it go, and look, it's still drifting, it's still moving, and so it's undergoing an angular velocity of 5.29 degrees per second. So it has a rotational speed, which is measured in how much of a circle it's completing every second. And that is the same for both the ladybug and the beetle. Now, the ladybug won't have to travel as far, so the ladybug's linear speed is smaller because it's covering that circumference, which is a smaller circumference, in the same amount of time that the beetle is covering this circumference. So linearly, their linear speeds, the beetle's linear speed is greater than the ladybug's, simply because it's got to go farther in the same amount of time. But they're passing through the same number of degrees in the same amount of time, so their angular speed is the same. More on that conversion right now. Whereas they are both undergoing the same angular speed, the linear speed is a function of the radius, how far this object is from the center. And so the conversion between those two is relatively straightforward. The linear displacement is simply going to be the angular displacement times r, times the radius. That's convenient. The linear velocity is going to be the angular velocity times r. Well, that's easy. The linear acceleration is going to be the angular acceleration, yeah, you saw it coming, times r. So there's relatively easy to move from rotational values to linear values. They're just different by the proportion of r. So let's see how this plays out. We're calling this rotational kinematics, and there are a lot of kinematics formulas that we're familiar with. Let's see how these play into rotational motion. Now, the good news is it should be really, really similar. It's going to feel very similar. First, a little technology lesson. Spinning hard drives. I don't know if you've ever dug into a computer and taken this thing apart, but that's called a hard disk drive. And these silver-looking platters are metal or aluminum or glass or ceramic, and they're coated with a metallic substance that is magnetic, and they are read by this little wiggling head. It's in a lot of ways, it's very similar to a record player in terms of its physical layout. So the platter, when it's off, is not spinning, and when you turn it on, it spins up. And typically, a typical hard drive spin speed is 72.
We are a go.
It's gonna blow up.
Let me touch it.
Eye protection. That's what, 20 gigs?
Yeah, right around there, 23 gigs.
That'd be so cool if you had super secure information. RPM. You just need to keep it. And it can go from being off to being at operational speed in about 7 seconds. So let's try and crunch a couple of numbers. What is the angular speed in radians per second when it's at full operational speed? Well, at full speed, 7,200 RPM. Well, RPM itself stands for rotations per minute. And one rotation, we can convert that to radians. Well, one rotation, that's 360 degrees. That's 2 pi. So one rotation is 2 pi radians. 1 minute is, as you're probably familiar, is 60 seconds. So I'm going to substitute these values in for rotations and minutes. So we got 7,200 2 pi radians over 60 seconds, and that gives me a value of 754 radians per second. And typically, people don't often think in radians. It's easier, we're just generally more familiar with degrees per second, but that's not what we're going to be working with. But one way of thinking about it is in a circle. Let's redefine a radian. A radian is, if you had a circle of radius r and then made an arc length that was a length r, the size of that slice of pie is 1 radian. That amount of displacement from here sweeping out to here is 1 radian. And so there's roughly, think of it like a big piece of pizza. Usually a pizza has 8 slices. This one's only going to have about 6 slices. So, bigger than your average slice of pizza. That's what a radian is. So it's going to cover 754 of these every second. And for the curious, if we divide this by 2 pi, we would actually find out the number of rotations per second. We can kind of play with our numbers all we like. 754 divided by 2 pi is about 120 rotations per second. Well, duh, that makes sense because 7,200 rotations per minute, divide that by 60, you get 120. All right. So far, math works and everything fits together. So that's the angular speed in radians per second, 754 radians per second. What's the angular acceleration? Well, you're probably familiar with the linear acceleration formula. Acceleration equals Vf minus Vo over t. Here's the part where things, as foreign a perspective as this is, things get really easy, because in the same way that each of these values, linear values, correspond to have a rotational analog, so do the equations. Linear acceleration is Vf minus Vo over t. Angular acceleration is, well, substitute all of the angular values in the same way. Rotational velocity minus final minus rotational velocity initial over time. The displacement, VOT plus 1/2 AT squared, well, the angular displacement, delta theta, equals omega initial times time plus 1/2 rotational acceleration times time squared. So they are perfect analogs of each other. If you know the values you're working with, the equations are exactly the same ones that you're familiar with, just with their analogous variables. So angular acceleration is omega final minus omega original over time. Now we just found our final velocity. That's 754 radians per second. And it started from rest, it was off. So minus 0 over 7 seconds. And that is going to give us an angular acceleration of about 107.7 radians per second squared. Our third question is, what angular displacement does the disk undergo during spin-up? How much rotation does it do? Well, we get to put in our rotational displacement formula. Delta theta, the change in rotational position, change in angular position, is equal to the original angular velocity plus 1/2 angular acceleration times time squared. And the original angular velocity was 0. So we're just left with 1/2 times angular acceleration, 107.7, times time, 7 squared. And that gives us an angular displacement of 2,639 radians, which, if we divide it by 2 pi, is approximately 420 rotations. So from off to full speed, the disk is going to spin around 420 times in order to get up to its full rotational speed, full operational speed. So far, take a breath. Perspective taking is going from linear quantities to angular quantities and back is just done by a factor of the radius. If you don't have to do that, if you're just dealing exclusively within angular quantities, the equations that you're going to use, the kinematic equations that you're going to use, are exact analogs of the ones you're already familiar with. So you got that going for you. All right, now you might see right down here, it says 3 kinds of acceleration. Yeah, here's where your head's going to spin. Ooh, yeah, I did it. All right, so consider the same hard disk drive. Let's now think about a speck of dust that's on the outer edge. We're actually going to concern ourselves with how fast, linearly, that object is going, the little speck of dust is going. Let's say at a time of 4 seconds. So partway through the acceleration process. So first, what's the angular velocity of the speck of dust at 4 seconds? Well, at time of 4 seconds, we would like to know the angular velocity, and that would be found using the original angular velocity plus acceleration times time. Oh, look how familiar that is, right? Vf equals Vo plus At, right? Exactly the same. Well, our original velocity was 0, so we're left with acceleration, which was 107.7 times the time, which was only 4 seconds. So at a time of 4 seconds, our angular velocity is going to be 430.8 radians per second. It's still speeding up at this point, but at this very moment, that's how quick it's spinning. We'd like to know the linear velocity. All right, so at that particular spin speed, how fast is this thing moving in that circle? Here we get to use our sort of conversion, our going from angular to linear. So velocity equals omega times r, and this disk is called a 3.5-inch hard disk, which is the diameter of the platter, 3.5 inches across there. Cut that in half and convert to centimeters. That's 4.45 centimeters, or 0.0445 meters. So we got our angular velocity, 430.8 times 0.0445, and that gives 19.17 meters per second. So we got a little speck of dust on the outer edge of this little spinny disk. If you sent it in a straight line, it would be going almost 20 meters per second. The width of our classroom at Newton North is roughly 10 meters. So that speck of dust is crossing 2 classrooms in a second. That's how fast the outer edge of this disk is moving. And it's not even up to full speed yet. It's only halfway there. It's only 4 seconds into its acceleration. All right, now, part C, what is the linear acceleration? Well, again, we're going to repeat what we did, sort of. The linear acceleration is the angular acceleration times the radius. The linear acceleration is going to be 107.7 times that radius, which is 0.0445, for a linear acceleration of 4.79 meters per second squared, which actually kind of seems sort of small. Like it's not picking up linear speed that much, but partly that's because it's a relatively small object. It's only this big. It's not picking up that much linear speed each second because it, compared to, I don't know, the tire of a car or something much larger, it just doesn't have far to go. Now, let's try something that we are familiar with because we've been doing it a lot lately, the centripetal acceleration. Centripetal acceleration is v squared over r. So here's where we have to distinguish between a couple different kinds of acceleration. We're going to call this perpendicular acceleration, this one for part C, the linear acceleration, as if it were moving in a straight line, how much speed would it be picking up in that straight line? If you were using this to, if you're using this to spinning the edge along a very long tablecloth to collect the tablecloth, a massless tablecloth, it's going to accelerate the tablecloth towards you at 4.79 meters per second squared, which is not nothing, because if it's a long tablecloth, it's going to be coming at you pretty fast by the time it's all done. But that's the linear acceleration. It's how quick that point is picking up its linear speed. But it also has some force exerted to it just to prevent it from flying out of the enclosure. It's got to be some rigid material to stop itself from exploding as it's spinning at these speeds. And so let's see, what is the acceleration, the centripetal acceleration on this particle. So maybe if I redraw it at this location here, granted it's not, you know what I'm going to do? I'm going to draw it more like a circle. So the linear acceleration that we've just found, acceleration tangential or acceleration perpendicular, it's perpendicular to the radius. That's not better. What we are now going to find is the centripetal acceleration. What is the acceleration that is keeping it in the circle? And that is the v squared, the linear velocity squared. So that's going to be 19.17 squared over the radius, 0.0445. And that gives us a centripetal acceleration of 8,259 meters per second squared. That really is dominating. For an object with different geometry, if it was a physically larger object, this radius would be larger. That would make the linear acceleration larger. This radius would be larger, and it would make the centripetal acceleration smaller. So this huge difference is not a universal truth among all spinning objects. It's just true for this one because it's physically small. It has a very small radius. But a larger object would be undergoing greater linear acceleration because it would have farther to go around the circle, but there'd be less force needed to keep it in the circle. It would be undergoing less centripetal acceleration. And we're almost to the end. So far, we talked about rotational acceleration. We've already had some background in centripetal acceleration, and now we're adding in tangential or linear acceleration. We're going to consider two of those right now for question E, our last question, which is what is the so-called total acceleration? The total acceleration is going to be the vector sum of these two. The vector sum of these two, which have the same units, meters per second squared. Can't really add two things which have different units. So I realize this is not going to be at all to scale, but I'm going to redraw these closer, where the centripetal acceleration is a very, very large value and the tangential acceleration is very, very small. And so we can probably tell that the vector sum of those two is really going to be dominated by the centripetal acceleration. But that's what we're looking for when we are asking for the total acceleration. It's accelerating in two directions. It's accelerating linearly. Its edge speed is increasing, but as it does so, it's also got greater centripetal acceleration. So it's experiencing both of these at the same time. And so those are orthogonal. Those are at 90 degrees to each other. And so that's just a Pythagorean theorem. So we got 8259 squared plus 4.79 squared. Square root of that whole thing, 8259 squared plus 4.79 squared, square root of which is 8,259.001. Yeah, so pretty much unchanged, 8,259.001 meters per second squared. So using this example, that calculation is not that interesting or revealing, but something to note is that once this device reaches its full rotational speed, that tangential acceleration becomes non-existent. It's the point on that outer rim of the circle is not speeding up anymore. It's maintaining a constant linear speed. And so the only acceleration that it would be experiencing once it reaches its full speed would be just the centripetal, because it is still going in a circle. So that's quite a lot, quite a mouthful, but I hope these example problems provide guidance for the future examples that you're going to see.